Good morning, everyone. My name is Timothy Lee Grant, and I am currently halfway through my machine learning class, which I am taking this term. And I decided that it would be a pretty good idea if I did an update video and talked with you guys about some of the topics which we are covering in the class. I think it would be pretty good for people who are also interested in pursuing machine learning to know what a standard course in machine learning actually covers, and so that they can go and look up those algorithms and methods themselves as well. So the first one that we discussed was k-nearest neighbors. And the idea behind this one is that if you have a whole bunch of data and you look at the attributes and find out the label. So the label is the predicted output. That's what you're interested in. So you have a whole bunch of data, and then, for example, what we did was we looked at census data, and you have all of the people's information, like how old they are, how many kids they have, all of this information. And then the end of the row was if they make over or under $50,000. And this is what we want to predict. So the idea behind k-nearest neighbors is that if you have a new point and you're given all of this data, it is probably going to be similar to data which is close to it. So if you only have one attribute, like the height, right? You might say that their income is similar to other people whose height is the same. So now that's one data point is the height. So you take a whole bunch of people, you plot their heights, and then you get a new point and say, okay, his height is this. Now, how much does he make? Like that. But in this situation, it's not only height, it's also age and gender and all of these different attributes that the US Census has. And so what you do is you take in the data, and then you get a new point and you say, okay, out of that, which one is closest to it? And you say, oh, this particular person, maybe like person number 1568 is really close to my new point. Now, what was person, whatever I said, 5628? What is this person? Is he over or under 50,000? And you say, he's under. Okay, then therefore my new point is also under. So that's how it learns. It's not actually learning. It's just looking at the data which it has already and saying this new point is pretty close to something that I already have, and I'm just going to take whatever I already have, whatever that prediction it, or whatever that person is. I'm going to say that this new point is very similar to it, and therefore I'm going to predict the same value. And then you can make it slightly more complicated by saying, okay, well, I don't want just the nearest point. I want the nearest 3 points or nearest 4 points. So, okay, this person, that person, the other person, and a different person. These are the 4 closest people to my new point. Well, let's average them. Actually, you probably do 5, right? Because you want to do an average and pick one. So 5, there are 2 that are under, 3 that are over. So therefore, I'm going to say this new point is over. Like that. So that was k-nearest neighbors. And then what we did was logistic regression, or just regression in general. So the idea behind this is that we want to classify if something is what we did was, is something cancer or is it not cancer? So you are able to, the basic idea is it's just like graphing, essentially. Like, you create a line, a decision boundary that says yes or no, and you use a logistic function, and the logistic function is kind of trying to map probabilities, so it forces the probabilities to be between 0 and 1, and it gives a decision boundary which cuts the data into 2 regions. So it's a straight line that cuts the data into regions, and it says anything on this side of my line is, maybe I should do it this, anything on this side of my line, which goes this way, is going to be classified as yes, this side is going to be no. And then you can do it in multiple different dimensions, but it has to be a straight line. So that's kind of the drawback to this, is that you have to have a straight line, and so you're fitting. Here's like your two-dimensional graph, right? And you might have data points blah 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 blah, and then other data points blah 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 blah. Here's yes, here's no, and you want to split a line right here that cuts it in between and says anything on this is one, is I think I said no, right? So it's going to be zero. Anything here is going to be one. So that's how you do that. But this is only two-dimensional. Then you can imagine like three dimensions, right? A cube, and you want to have a plane which cuts this cube in half, and you have all of these are going to be yes, the other ones are going to be no. So that's logistic regression, and logistic regression is super important because it goes into the next one, which is neural networks. So neural networks take logistic regression and then say, okay, what would happen if I took one logistic regression and stacked it on top of each other, and stacked another one on top of each other? So each little neuron is actually a logistic regression function. That's all it is cutting your space into half and saying, okay, anything on this side is yes, anything on that side is no. But then, okay, if you do this, you can create another one like that, right? All of a sudden, it's not just a straight line. It's kind of like this you have a thing down here, 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 right? So what you can do is you can string these logistic regression functions together, and then it's honestly kind of difficult right now. I'm myself trying to understand what's really going on with the neural networks. That's the topic which we are covering right now. So what we do is you have input right here, and it has a whole bunch of different like input values, right? And then it goes through this neural network to an output, and it predicts. What we're doing is handwriting numbers. So you have the input for a single instance is going to be all of the like pixel values which is present in that little photo, right? So you have a photo and it has a 5 right here. And so it has each pixel value in this grid has a certain number associated to it. Like if it's black or heavy dark, right? It's going to be higher. If it's pure white, it's going to be 0. So that's the input. And then it comes out to the end, which has 10 different neurons. And each of those has a probability. So it's either like, for example, the first node is going to say how much or what probability this number is a 0. The second node is going to say what probability that this number is a 1. Okay, so what you do is, let's say you feed a 5 in. Okay, you feed a 5 in, and it comes out, and the activations on the output come up haphazardly and ridiculous, right? It says like it's a 80% chance that it's a 5, or a 80% chance it's a 2, a 20% chance it's a 7, a 98% chance it's a 0. So you have all of these, and you try to figure out like, that's interesting. How do I get the 5 to have a higher activation? So what you want to do is you want to figure out how you get that 5 neuron to have a higher activation and all of the other ones to have a lower activation. And if you think about it, we use the gradient, which you try to figure this, and this is one of the mind-bending things. It's like you're not taking a derivative of a function. No. This is a static number that you're trying to take a derivative of. And so what you can do is the previous node, okay, so here's the output. Here's what you want. It's a 5, right? We put a 5 in, and it filters through. And here's the last node. This corresponds to the 5 node. Okay, and now it has inputs coming in here. Now, what you can do is you can take each one of those neurons, which is connected to the 5, and say, okay, what did you come in with, right? And what is the difference between what you should be and what you are, what you were when you came through, right? And then you can say, okay, well, I want to increase that. So then you just adjust the weights, which the weights, I didn't really talk about that. It's in the logistic regression. You remember, like, each of these neurons is a logistic regression function. So what you can do is adjust it's W, which is a weight matrix, and that's multiplied with X, which is your inputs. And then you have a plus B, which is the bias term. And so that just creates the line. That's just a multi-dimensional plane, right? So if you remember, like, if it's one dimension, the weight is going to be some value. X is going to be the slope, right? So the weight, mx plus b, right? So m is the slope, x is that variable which you are taking the slope of, and then plus b is the bias term. And then if you want a plane, you actually have two. So you have the first weight times x1, the second weight times x2, and then you have your bias term again. Okay, but you can abstract that to multiple dimensions, right? So each one of those neurons has a particular weight vector which gives off what it will, what percentage it says that it is, either a 0 or a 1. So it says a high probability that it's a 0 or a high probability that it's a 1. If you want this 5 to be higher and there's a connection between it, and you say, okay, I want this to be higher, I need to adjust the weights of this incoming neuron so that it actually does fire correctly. So then you change the weights such that this one causes the 5 to light up more. It has a higher probability. But then you also want to take into consideration that the other ones need to be a lower, because it's not any of the others. You want the 0 to have a lower probability. You want the 1 to have a lower probability. You want the 3 to have a lower probability. All of those. You only want the 5 to light up. So you have to change all of the different activation, the weights, well, and the biases, such that you get a 0 0 0 0 1 0 0 0 0 0, kind of like that. So you put it in, you figure out, okay, well, here's at this last layer, it is a particular instance of 0, like probabilities. Then you look back that one layer and figure out, okay, now how can I change the weights on all of these incoming neurons such that we get a 0 0 0 1 0 0, kind of like that, right? So then you figure out what this one needs to be. Okay, then you work backwards. The next one, you say, okay, now how do I make this what it needs to be? So then you change these weights and biases. And you say, how can I change this one? You change these ones, right? And all the way until you get to the input. And then, so now that's how you do it's called backpropagation. That's how you backpropagate all of the weights, and you slowly over time. So you have, that's just one. You put in a 5, then you put in a 2, and you say, okay, well, now it should be like this. Let me change the weights. You put in an 8. Okay, let me change the weights. You put in another 8, and it comes out to something else, and you say, okay, now how can I change the weights? And you do this like thousands and thousands and thousands and thousands of times, and then you keep tuning your weights and biases until you create it's just a neural network which is has a particular values of weights and biases. That's all a neural network is a connection with neurons with logistic regression functions cutting the space in half, and you're tuning. Okay, is it like this? Let's Here's a weight which is higher, here's a weight that's lower, then your bias term, that's all it is. And then you feed it through, and then it comes, or sorry, you feed it through, see what the output is, see what it predicts, and then you back propagate using the chain rule, gradient chain rule, right? And that's how you improve your biases or weights and biases. So it's an extremely interesting topic. And honestly, I'm having a fair bit of difficulty really understanding what's going on. I spent so much time looking at the code and just trying to get it to uh, fit in my head. Like, I already got the assignment working, right? Like, I can turn it in right now. I can get essentially 100% on the assignment. I did the assignment, but there's so much that is all I had to do was fill in some formulas. Actually, it was kind of easy. There's so much more that, like, the professor wrote the a lot of the skeleton code, and I'm trying to go through all that skeleton code and figure out what on earth is going on, like how it's working. It's really, really, this is a pretty dense topic, but I am going to keep trying to figure out how exactly it's working. I haven't had that much time. It's like a week learning it. So, and I've also had a fair amount of other classes that I'm putting time into. So yeah, that is neural networks. And then now we are just getting into decision trees. And that one is that you can figure out if your data has something that is characteristic to decide if it is a particular class. So you take cars and you look at different attributes of them, like the make, the model year, and then you just try to, like, essentially say, okay, it's think of like a circuit almost. Say, like, it's a logical expression. It's not really that difficult. It's just saying, like, if your car is a Mazda and is made in the year 1993 and is the color red and something else, right? It's just an composition expression, logic expression. And you just keep going until you find a definitive, okay, from my data, all of the cars which I have seen that match this expression, this logical expression, are this. Maybe fuel efficiency over or under whatever you want, or a price, right? Over or under $10,000, right? So you say, okay, this and this and this and this has or has accurate, has sufficiently, that's the right word, has sufficiently characterized all of my training examples as this. So therefore, I'm going to label it as this. And then you do more and more logical expressions until you classify all of your data. That's that. The decision trees are kind of, I don't know, so far they're kind of boring to me, but the neural networks, man, that stuff is interesting. I'm really excited to learn more about it. It's really difficult, and he has been telling us a whole bunch of other stuff about, like, if you take a neural network and then make it really deep, so you add more and more layers, that it tends to not overfit your data, which is very interesting about why that would be the case. To me, it seems like as you add more and more logistic regression functions, it's going to fit your training data really well, but then it's going to overfit completely. And what he was saying is that this is not actually the case. So I'm kind of curious about like why that is. Anyways, thank you guys for watching this video, and I hope that you guys have a wonderful day. I will see you guys later. Bye.